So today we're going to be talking about the beginning of Unit 6, which is dealing with right triangles. We're going to spend some time today talking about the Pythagorean theorem, and then next class we'll get into 6b, which is classifying triangles using the converse of the Pythagorean theorem. We're also going to spend some time today reducing radicals as well. So I want us to look at this first problem, and I want us to read it first. It says the fire department is fighting a fire. If the ladder is 10 meters tall and the distance from the foot of the ladder to the building is 5 meters, how far up the side of the building can the ladder reach? So what I want you to do for example 1 in your notes is I'd like for you to copy down the picture that is associated with this problem. The picture should look like this. The ladder is the 10 because it says that the ladder is 10 meters tall. The foot of the ladder is the distance from the foot of the ladder to the building is 5, and we're looking for how far up the side of the building can it reach. So this is the example I'm looking for. We have side measures of a right triangle, so we are in fact looking to use the Pythagorean theorem. So we need to remind ourselves what A, B, and C are. Remember that the C is always going to be the hypotenuse, and the hypotenuse is going to be across from the right angle. So I know that it's going to equal 10 squared. A and B are just the legs of the other two sides. So what we're looking for here is we're looking for the formula, move my little guy here, of 5 squared plus x squared is equal to 10 squared. So then we're just going to simplify 5 squared, 10 squared, we'll subtract 25 from both sides, and we should get that x squared is 75, and then it's a matter of trying to reduce the square root of 75. So I need to be able to reduce that. Now, I've already done the work here, but how did I get 5 square roots of 3? Because at the latter half of class today, you're going to be reducing these radicals. Remember when we did this earlier in the year, we made a factor tree. 75, and I found two numbers that go into 75, 25 and 3. We know that 25 can be broken down into 5 and 5. And I bring out that pair. I bring out the 5 outside of the radical, and the 3 stays underneath the radical. So that's what I'm looking for. I can also check using my calculator to make sure that I've reduced it correctly. So if I go on my calculator and I type in the square root of 75, and I also type in 5 square roots of 3, I should get the same answer. So I want you to be checking to make sure that you've reduced it correctly. This particular problem can be written in 3 different ways. All 3 of these answers are correct. Square root of 75, 5 square roots of 3, and 8.66. The 5 radical 3 is called the reduced radical form. You're going to practice that more later this class. But you can also write your answer. If it asks you to write it as a decimal, 8.66 would be fine. Let's try another example. Let's try example 2. So I would like for you to put this picture in example 2 into your notes. This picture here that I have on the right-hand side of the screen. What is the measure of one leg of a right triangle with one leg of 2 units and a hypotenuse of 7 units? Notice the hypotenuse is the longest side. It's the side that's across from the right angle. So that's why I've labeled it 7. The other 2 sides are 2 and x. When we put these numbers inside our Pythagorean theorem, you have over here on the left 2 squared plus x squared equals 7 squared. Remember that the hypotenuse is what goes on the C. Sometimes it's a variable, sometimes it's a number. Here it happens to be 7. As we continue to look at this problem, we're going to go ahead and simplify it. So I have 2 squared is 4, 7 squared is 49. Subtracting 4 from both sides, I get x is equal to the square root of 45. I would like us to practice being able to put the square root of 45 in reduced radical form. So you're going to need to make a factor tree. What numbers go into 45? 9 and 5. So when I do 9 and 5, I get a pair of 3's come out and a 5. So that means that 3 radical 5 could be a possible solution. Notice on the right-hand side, I've chosen 2 different numbers, 15 and 3. They also give me a pair of 3's and a 5. So it really doesn't matter what 2 numbers you choose. I happen to think using perfect squares, like 9 as a perfect square, makes it a little easier. But as soon as you get a pair, you can stop. So 3 radical 5. Again, you can test this. So if I test the square root of 45 and 3 square roots of 5, I should get the same answer of 6.7. So 6.7 would be the decimal answer. 3 radical 5 would be the reduced radical answer. We have one more example I'd like to be able to do with you, and this one's a little bit different. Example 3. So I want you to draw the picture that's associated with this problem. It says that Tanya runs diagonally across a rectangular field. Uh-oh, no triangle this time, but it's a rectangle. It has a length of 40 yards and a width of 30 yards. What is the length of the diagonal in yards that Tanya runs? So when we look at a picture of this, this is what we're looking for. A rectangle with a diagonal and a length of 40 and a width of 30. Notice that that diagonal cuts the rectangle into 2 right triangles. That's great. So what that means is that I'm going to use the Pythagorean theorem in this case to be able to continue. So 40 squared plus 30 squared is equal to x squared. We're going to head and reduce 1600 and 900 is equal to x squared. Combining like terms, x squared is equal to 2,500. Taking the square root of both sides, and I do get that x is simply 50. So the length that Tanya runs is 50 yards. Now, on the right-hand side, I have listed some things called Pythagorean triples. They are simply numbers that satisfy the Pythagorean theorem. We'll talk more about this next class, but if I typed into my calculator, 5 would be the hypotenuse because it's the longest side, but 3 squared plus 4 squared should equal 5 squared. Let's just double check it. 3 squared plus 4 squared does in fact equal 5 squared. Same thing with 6, 8, and 10. Because 10 is the largest side, it's the hypotenuse. So 6 squared plus 8 squared should equal 10 squared, and it does. We'll talk more about Pythagorean triples next time, but they're all similar triangles, which is interesting. At least these 2 are. Right, so at this point, what I'd like, we have to do one more problem, and I'm going to actually change this just for a second. I'd like to go back and redo it, so do it with you if that's all right. So in this particular problem, I have an example. This will be example 4, and then we're done copying examples down. I'm trying to find the area of this triangle. It's an isosceles triangle with the sides are 6. I know that my area of a triangle formula is 1/2 base times height. If you remember, the base is going to be 8. And we also use the word height of a triangle a long time ago. We called that the altitude. So we need to figure out what the height is. The altitude divides the base into equal parts in an isosceles triangle. So now, if you look, we have simply a right triangle that I can figure out the height for. Well, the height squared plus 4 squared is equal to 6 squared. That tells me that the height squared plus 16 is equal to 36. I'll subtract 16 from both sides. The height squared is 20. Therefore, the height is the square root of 20. I'm not going to reduce this one because I'm just going to put it in like it is to get my final answer. So I'm going to plug in for the height the square root of 20. The base, if you remember, was the entire base, which was 8. And then I have a half. And when I type all of these numbers in, 1/2 times 8 times the square root of 20, I get 17.9. So the area of my triangle is about 17.9 units squared. At this point, I want you to pause the recording. This is, so go ahead and pause it. And we will pass out the first set of problems that I'd like for you to complete. Make sure that you turn in those problems 1 through 4. You should turn those in. 5 and 6 we'll do next class. So collect those now. We're going to spend the rest of class today looking at reducing radicals. And you have 20 problems to complete where we will do today, you'll turn these in, these radicals. I've done a problem already, but I'd like to do a couple more just to remind ourselves how to reduce radicals. So here's one example, the square root of 200. I know that 100 and 2 both go into 200. 100 is reduced to 10 and 10, which is a pair, so I'm going to go ahead and stop. And I'm left with the 2. So this becomes 10 on the outside because the pair goes on the outside of the radical, and what's left goes underneath the radical. So my answer is 10 radical 2. You can double check both of these on the calculator by just typing them in to make sure you get the same decimal. Let's try a little bit more of a difficult one. Okay, I'll erase this real quick. Let's try the square root of 486. I need to decide what numbers go into 486. 486 divided by. I'd like to try some perfect squares, like 4. Doesn't go into it perfectly. The next one I might try is 9. Well, 9 does work. So let's look at 9. It's 9 times 54. Why did I want to use a perfect square? Because it gives me a pair. That tells me that that number goes on the outside of the radical. Let's keep reducing 54. That would be 9 and 6. Again, I have another pair. So it's going to come on the outside. The 6 just becomes a 2 and a 3. These go on the inside of the radical. When I simplify it further, 3 times 3 is 9, and 2 times 3 is 6. So the reduced radical of 486 is 9 square roots of 6. Let's double check that. The square root of 486 is the same as 9 square roots of 6. They are, in fact, the same. So you're going to now look at the 20 problems and that you're going to be doing. The sub will pass those out. You're going to need to show your work doing the factor trees on a separate sheet of paper. Make sure that you're transferring your final answer to the actual sheet itself. Please know ahead of time that there are multiple versions in the classroom, so that you should not be looking at your partner's, your neighbor's work. Do your own work, show your own factor tree, and make sure that you turn this in at the end of class.